Hi there. We're going to talk about our equilibrium unit. We're starting with the first bit of the equilibrium unit here in chapter 13. I have got the slides here that are the official slides from OpenStax, and I'm using those just simply to give us a little bit more organization to the talk, and you'll be able to refer to it. You see the screen numbers here, the slide numbers rather, and so we can make reference to those as we're going along. You'll also be available to see this in our OneNote file, so you've got that as well. So we're talking about equilibrium in chapter 13, and the sections of that chapter are given here. There is a little introduction that I say before won't make much sense, but let me just explain a little bit about it. The reason it doesn't make much sense is we haven't done chapter 12 yet, which is the energy chapter. But if we think about these reaction coordinate diagrams that we've seen before, so these all have the reaction coordinate on the x-axis, and then on the y-axis we're going to have energy, which we're later on going to define more fully in the next unit about how we talk about energy. And we've talked about basically something looking like this, where this is our reactant labeled R, this is our product labeled P, and this hump in the middle is where the transition state is, and the distance from there to there is the activation energy for the forward reaction. And if I change colors here, I'll do it in green. The distance from up there all the way down to here in green is the activation energy for the reverse reaction. Switching my color back here, I won't label them all on every one of these, but so that the first one's a case where the products are lower in energy. The second one is a case where the reactants and products are at the same energy pretty much. And then the third case will be one where the reactants are much lower in energy, the products are higher. In the first case, this is going to be one where the equilibrium favors the products, and so we're going to talk about an equilibrium constant capital K as opposed to the lowercase k for kinetics. And here K would be much greater than 1. Here K is going to be equal to 1 where they're energetically the same, and here K is less than 1 in that case. So that's kind of what the first part of the intro is talking about without getting into the definitions of everything about energy that we'll be doing in the next unit. So like I said, it'll make much more sense after the next unit. So this one of the advantages of using their slides is that they have images from the textbook. This shows the some of the equilibria that are associated with the stabilization of the pH in the bloodstream. So you've got cells, you've got some sort of blood vessel there with carbon dioxide and water in equilibrium, forming something called carbonic acid, which then is in equilibrium with something called bicarbonate and the hydrogen ion. And we'll see more how that goes, but we're trying to understand that kind of thing. So chemical equilibria down here on slide 4, we're talking about what are you trying to do? Well, you're going to basically appreciate the difference between an equilibrium reaction and a regular chemical reaction. So basically what we're looking at is reactant going to product fully versus this equilibrium situation where not only can the reactant go to the product goes back to reactant, and we wind up instead of being governed by limiting reactant who runs out first, we wind up with some amount of the reactant and the product present when the equilibrium reaches that equilibrium. And it says that's dynamic. That means it does continue to go back and forth. So here's a classic equilibrium that we look at here. We've got dinitrogen tetroxide N2O4 in equilibrium with NO2. And so one N2O4 makes two NO2s. This happens in the gas phase. Oftentimes initially with equilibria we talk about gas-based reactions. Eventually we'll be looking at these in aqueous systems. But that is an equilibrium. And one of the reasons we look at this equilibrium, as it says in slide 6 here, is that while N2O4 is colorless, NO2 is brown. And so we can follow this reaction by looking at the formation of this reddish-brown color that indicates the NO2, and use that as a way to follow the progress of the reaction. So here is an image from the book, and I've copied this image, I think, down here, so you have the color version of what's in slide 7 is down below here. So we start off, and you see it initially when time is equal to 0. At the start of this, we got pure N2O4, and you see there, if you look at those things closely, you've got 2 blue nitrogens and 4 red oxygens there. So we've got 1, 2, 3, 4, 5, 6, 7 N2O4 molecules. Then the reaction starts happening, and you start seeing the formation of the NO2 molecules, which just have 1 blue nitrogen and 2 red oxygens. And then if you look at the top up there, this tube is beginning to turn brown. So you're seeing a color change. And as the reaction proceeds on, it gets darker, right, at the end at equilibrium. So if we look at a graph of the concentrations, what you see is that N2O4 goes down and NO2 goes up. This is time versus concentration. And of course, we use this in chapter 11 to think about the rates, right? We look at like the slope of this line here and say that that was the rate of N2O4 being formed at that particular time. So this is the delta NO2 delta T. So we looked at this kind of graph before, and what happens is you see at this point here you reach equilibrium right here. So equilibrium is achieved at that point. And past that point, these levels don't change. They're not 0, though. Okay, so a standard R to P type thing that's going to go till one thing runs out. If we have concentration versus time, what's going to happen is if we have R here, R is going to run out, and P is going to increase and stop increasing when R runs out. That doesn't happen. It doesn't go to 0 here. 0 is down here. This is not 0 for N2O4 up here. The next bit of the slide is a little bit confusing, but they're trying to basically tie this back to rate. So the y-axis now is rate, not concentration. And so we've multiplied things by the forward rate constant and the reverse rate constant, and the orders are by the number of those molecules that are in the reaction. And what they're saying is that when you achieve equilibrium, the forward rate is equal to the reverse rate. And so that's tying equilibrium and kinetics together in that image there. So those kind of things are summarized here in slide number 8, where they talk about this. So what I kind of talked you through there is summarized again in slide 8. And just generally, if you see something in here that you're confused about and you want to see better images of it, you can look to the textbook, and frequently in the slides here you see it says figure 13.2, so you can find that in your textbook online. All right, so again, one of the points we want to make is that when you get to the equilibrium, the system is not static. That is, it isn't standing still. It's dynamic. It's in motion. So what's happening at equilibrium is not that the N2O4 has stopped turning into 2 NO2s. It continues to do that, but the rate that the N2O4 turns into 2 NO2, that is equal to the rate at which the 2 NO2s are turning into N2O4. And I guess I should say rate of. This is the forward reaction is equal to the rate of this backwards reaction. So it's not that, and they make a relationship to juggling. Juggling's actually kind of a neat skill to pick up. I learned to juggle when I was undergraduate, and you can easily Google how to do that. It's not that hard, and it's kind of cool. And I find it to be something calming. if I'm stressed out, sometimes juggling for just a little bit will calm me down. So, all right, so this is again another image that looks better in color, looking at an equilibrium mixture of liquid and gaseous bromine. So we're talking about Br2 liquid in equilibrium with Br2 gas. And I think I put the color version down here. Maybe I didn't, but the color version's in the textbook. You can take a look at that. All right, moving along into 13.2, we're going to talk about how to derive something called the reaction quotient. The reaction quotient, remember, is the answer to a division problem. It's given the symbol Q for quotient. And then we're going to also talk about something called the equilibrium constant, which we've mentioned before. That's a big capital K as opposed to the little k from the rate constants, and then relate the magnitude of that to the properties of the chemical system. See that intro slide where I talked about those charts, those reaction coordinate diagrams. All right, so this is our equilibrium symbol. Sometimes you'll see it written as an equal sign. That's not really great, but a lot of type fonts don't have an equilibrium sign in them. Sometimes you'll see people write it as a single double-headed arrow. I really don't like that. That means something else later on that you'll see in organic. So what I prefer to do is to write, two arrows like that, either half of an arrow, or you can make both of them like that either way for equilibrium, showing the reaction goes both ways. The reaction quotient lets us come up with a number based on the amounts of the reactions and products present at any point. And there's a pretty simple general scheme for it. What you're going to do is you're going to take the products, you're going to raise them to their coefficient, and divide by the reactants raised to their coefficient, and you have to do all of them. So product 1 times product 2 to its coefficient 2, and so on, however many you have. So you see here for MA plus NB, you see here's A to the M. This shows up here coming from that, and then up here this D to the Y comes from YD there. So that's the reaction quotient. This is sometimes called the law of mass action. Not a term I usually use, but you will hear people refer to it that way. And if you see a sub C on that, that means based on concentration, as opposed to, we'll see soon, based on pressure for that. Q is a number you can calculate at any situation. Concentrations are in molarity. When we calculate the value of Q, we actually kind of ignore the units. So I hope that's a refreshing break to you, that we ignore those units. And then you look at you calculate Q for a set of values for whatever the concentrations are at that point. And you can calculate Q at any point in the reaction. That's the whole point of it. We can calculate it any time. And we're going to use it to tell when we're reaching equilibrium. So here are some graphs of a reaction. This reaction is SO2 plus O2 in equilibrium with SO3, and I believe that's 2 and 2, and I think this is gas phase. Okay, that's a color version of the slide below. I think these are all gas phase. So Q for this is going to be equal to the concentration of SO3 raised to the power 2 over the concentration of SO2 raised to the power 2 times the concentration of O2 raised to the first power. So we don't have to calculate that. And if we calculated that value right at the point where you are at equilibrium, Q will be equal to the equilibrium constant at that point. And so this graph down here, the bottom one here, is saying this is the reaction quotient, and saying that at a certain time the reaction quotient equals this K, which is right there. So at this point, Q is equal to K, or at this point over